All right, our final speaker today is Eric Nost, a PhD candidate at the University of Wisconsin-Madison.
Thank you, Stephen, for letting me borrow your computer as I get a dual setup here. All right, so my presentation is a little bit different, but again, addressing the role of symbolization, and in particular in maps that are designed to be used by decision makers, policymakers, okay, specifically concerned with ecosystem services. Okay, so thanks for coming this morning. And just a caveat, right, this is research in progress. I really do look forward to any feedback you may have on where to go with this. What I'm doing is surveying computer models of ecosystem services for the kinds of cartographic representations they enable users to produce, the ways they symbolize ecosystem services and changes in those services, right? These models are often packaged with maps, charts, and other visualizations and have come to be known as, quote, decision support tools. They're expected to enhance and justify the translation of science into policy. But do models actually live up to these expectations as decision support? And even so, what kinds of decisions do they support? Those are the questions I'm asking broadly in this research. So what are ecosystem services? Well, they're the benefits, and this is a well-known common definition, right? The benefits that nature provides to society. For instance, coastal wetlands in places like Louisiana slow down storm surge and reduce flooding. Now, conservationists and decision makers would want to know about and quantify ecosystem services, measure them, in order to restore them or conserve them. In particular, decision makers might model services in order to predict future conditions and the trade-offs in ecosystem services provision between different future services. And I'm going to use ES as an abbreviation throughout this because it's long to spell ecosystem services, so when you see ES, that's ecosystem services. The dissertation work I am wrapping up is on the restoration of coastal ecosystem services in Louisiana. And one of the questions I asked is, okay, how do decision makers actually learn with the models they're using to do this restoration work? Mapping is fundamental to what they're doing. They're particularly interested in, this is, state regulators, state planners, in conjunction with federal agencies and engineering firms, academics. There's a whole team working on this. And the decision makers are particularly interested in, the planners are particularly interested in differences maps that illustrate changes between different scenarios and or over time, right? So while there are many constraints to mapping in general, a specific tension decision makers face with difference mapping is utilizing absolute values versus relative values. So what you're seeing here is an example, play it again, an example of model output predicting for a high scenario of future conditions, meaning climate change is going to get really bad over the next 50 years. Brown shrimp habitat and the changes in brown shrimp habitat across the coast. And if you're a shrimper, you harvest shrimp, this animation of differences in habitat over time isn't necessarily all that helpful because, well, it just tells you about the relative change, not how many shrimp are still going to be there or how many were there in the first place. In this next map here, or set of maps, small multiples, I guess, you actually see the actual value, right? And this is a habitat. It's an index value, right? So suitability. So it's where the good habitat will be and where it won't be. So you can actually compare values at particular places on the coast. A much probably more useful thing or more amenable to a shrimper, since that's your livelihood. You might look at a particular place. Beyond Louisiana, there are a number of ecosystem services models currently in use or in development, and actually half of federal funding for research on ecosystem services is dedicated to developing these kinds of decision support tools. which can range from being conceptual and focused to highly technical. And these are, I'm going to show two examples. This first one is Invest, which is a diverse set of essentially Python tools held together with a GUI. There's also Aries, which is a bit more integrated, but also a bit more complex. And advocates for these models and ecosystem services in general note their potential to effectively communicate nature's benefits, which are oftentimes ignored in policymaking, in ways that decision makers will understand and be able to act upon. However, much of the research is really focused on kind of the spatial analytical dimensions rather than the cartographic dimensions of ecosystem services models, right? So research has emphasized the capacity to conduct spatially explicit calculations, more so than map design considerations and understanding trade-offs between different map goals. But of course, we know from studies just of, for instance, sea level rise and other climate change maps that symbolization and other representation strategies shape what and how policymakers learn with maps. So in this specific project, I'm asking, okay, what kinds of maps do ecosystem services models produce, implying what do decision makers actually learn from them? I'm also asking, how is this connected to the ways in which the models and maps are developed, how their development is organized and funding, and how that development and funding might shape what kinds of maps are available. For the purposes of this talk, I'm going to focus, though, on the first set of questions. So what did I do? I conducted a survey of ecosystem services modeling tools and understand their mapping components and their symbolization strategies, right? The ways they represented geospatial data. To begin, I set to find as many of these decision support tools as possible, starting very broadly with the main criterion for inclusion essentially being that the tool be a model-based framework which frames decisions around ecosystem services for decision makers. Now, that excludes many research-oriented computer models, but it does, their main purposes are mainly research, but it does include many kinds of decision support tools. So conceptual models, databases, desktop and standalone models, ArcGIS plugins, and interactive web maps. And so I also aimed widely, because of my topical interests, including explicitly ecosystem services models, but also coastal planning tools that may deal with what I would consider ecosystem services, but not explicitly. So these are some of the sources I drew on for this survey. I'm going to skip over this real quick, but I can come back to it later. And I ended up with 74 different tools. I then whittled to ones that explicitly aim to model and/or represent ecosystem services. And based on their own self-description, 10 of these did not specifically mention ecosystem services, but did calculate things that we could consider ecosystem services, right? They didn't say, storm surge ecosystem services, but looked at storm surge, things like that. I deemed 29 of all the tools to explicitly model ecosystem services. 7 of those, though, were conceptual models or databases of ecosystem services values. Excluding those, so we've got 22, I determined that 19 had a mapping component, okay? Usually through some kind of GIS plugin. 1 was proprietary, 2 were in development or in general, so I excluded those. So I ended up with 16 model or model-based mapping applications I could review. What surprised me, though, was that 7 of these were actually web maps or models that fed into online web map dashboards. So web maps suggest a certain ease of use for decision makers, right? Either you can just upload your results into the dashboard, right? You don't need to know GIS per se, or the data is already assembled for you on a website. For the purposes of this presentation, then, I'm going to focus on these 7 web maps for ecosystem services planning. I analyzed 6 out of 7 as 1 was only available with the use of an iPad, which I did not have access to. And just topically, 1 of the 6 was specifically coastal, 2 are forest-oriented, and the rest were kind of general, no specific ecosystem type. Here's a few examples of them. iTree Landscape, which allows you to do planning around urban forests. The Virginia Department of Forestry's Forest Planner does similar things, calculates ecosystem services, but for forests anywhere in the state. The Nature Conservancy's Coastal Resilience Tool, which calculates lots of different things, but including ecosystem services. So what would we want to know about these tools? So based on interviews with decision makers in my work in Louisiana, experience in using some of these tools in the cartographic literature, I proposed 4 factors to evaluate these 6 tools. So scale first is really, for me, an issue of aggregation, right? At what geographic levels are the data aggregated? There's a really important difference between just loading an entire database of point data and aggregating that data into various aerial units. This is in part because we know users, including decision makers, like to be able to talk about things at different scales, right? General trends and specific sites, and for different units, okay? So properties, census blocks, watersheds. As a kind of an aside, the modifiable aerial unit problem is an issue here, right? So the size of the unit of analysis skews your results. That's more of an analysis problem, so I'm going to set this aside. But it does come into play with the site-based ecosystem services assessment tools. Uncertainties, right? So there are several kinds of uncertainties that may be present in ecosystem services analysis that decision makers would want to account for and that may or may not be represented by the map. Color, so mapping coastal ecosystem services in Louisiana often relies on a red to green, land loss, land gain kind of color scheme that can be challenging, especially when overlaid against satellite imagery. So, what are the default color scales that these web maps rely on? Are they appropriately diverging or sequential? Can users change them? And as I mentioned earlier, decision makers, so this last factor, change, are particularly interested in being able to see predicted differences over time and differences between scenarios. In many contexts, right, they're responsible for evaluating potential development or restoration impacts and must be able to rationalize their choice. Many of the models behind the web maps, if not the web maps themselves, enable users to generate scenarios. But in what ways do they help users actually visualize these? In side-by-side layouts or small multiples, or through one calculated value on one map? So here's a summary of here are the results for kind of the summary information, right? So, they're all about informing planning decisions. Their spatial focus range from the kind of site-based assessments to, calculating a whole region of the planet. They also applied from different places, right? So the Virginia tool, the Department of Forestry tool, was only available for Virginia, while there are other tools that can work across the US, and there are some that can work across the globe. Most of them enabled prioritization type decisions, right? Where's the best place to protect this service? Many of them also allowed scenarios, often developed with nonprofits or by government. Most of them kind of focused on a few, 3 maybe, ecosystem services, and surprisingly, all of them except one was open source and open access, right? And even the one was more of a freemium model. So in terms of the cartographic components here, so yeah, in terms of scale, one enabled changing the unit of analysis, right? So you could aggregate things differently between the census block group or the county, for instance. One re-aggregated data depending on what zoom level you were at. We'll see that in a second. In terms of uncertainties, only 2 explicitly visualized uncertainty. Only 1 explicitly visualized uncertainty, but 2 got it in a different way. They either provided access to different scenarios, right? So you could toggle between scenarios and kind of clue yourself into, well, there's an uncertainty depending on what future climate change scenario we see, whereas one displayed, pre-modeled uncertainties, right? Like, we conducted this model analysis, and here's where we're uncertain about things. In terms of color, one of these web maps allowed users to change the color ramp. 2 had kind of toggles for transparency. In terms of change, only 2 enabled any kind of differences map. So being able to change, to see the change in ecosystem services value between now and some future, and they did that in different ways. So to kind of dig into this, I'm going to explore a case using one dashboard from the INVEST suite of models. So INVEST is a suite of 18 different ecosystem services models They all produce maps as outputs, shapefiles, and at various scales. Okay, so it used to be an ArcGIS plugin. Now it's kind of its own open source standalone programs. And you can upload model results, outputs, into interactive web maps for the coastal vulnerability and habitat models. Okay, I'm going to talk about coastal vulnerability in particular. In general, for those two dashboards, the results are very similar, or actually they depend on which dashboard we're talking about, but they both only kind of visualize one scenario at a time. So this is the coastal vulnerability dashboard. Okay, so in terms of scale, we see these pie charts, which, if you zoom in, ultimately resolve into points. As for uncertainty, the model doesn't provide any measures of uncertainty, so they're not represented or symbolized here. But there is an estimate you could, because this looks at sea level rise. In terms of color, there's a tan to red ramp here that indicates exposure, coastal exposure. And in terms of change, the web map only accepts one scenario at a time, but you can compare coastal exposure with and without habitat, since this is a calculation the model makes. You just can't compare exposure at one scenario with exposure at another scenario, which you could, because you can create separate model runs with different parameters. Okay? To further explore the feasibility of mapping differences and some of the design trade-offs that come with it, I conducted a kind of experiment. I built a web map that takes two or more scenarios and allows for comparison, right? Either side by side in kind of small multiples or directly valued. So again, the original coastal vulnerability dashboard lets users compare coastal exposure rankings between habitats as they currently exist, and if all the sea grasses were taken away. But what about something in between? And what about different ways of visualizing that difference? So the tool I created here enables users to visualize exposure with and without habitat, but in different ways. So they can view the current exposure, and just to note, I've reclassified things a bit and changed the color scheme just for my own purposes. Then they can view the exposure without habitat on its own. Users can also click to see the scenarios side by side. So in order to judge potential differences that way, as you see there, this allows direct comparison and retains the original classifications for each scenario. So users might zoom in and might notice some areas where points have changed in each class. But because of this particular data, it's a little challenging to see the differences. One way to overcome this is to display the value of these differences themselves, right? So zooming out, the user can confirm that relatively this particular area did see a noticeable change in exposure between the two scenarios. Of course, with this insight, they lose knowledge of the absolute values of exposure, and enabling retrieval can be an interaction strategy for overcoming this. So you can click on a point, like here, that displays the changes in absolute terms and confirms the relative change. So, in this case, the variables is coastal exposure. Like the shrimpers in Louisiana I began with, we can imagine coastal residents wanting to know absolute values, right? How much shrimp is going to be there? How exposed am I going to be? Because after all, it's that amount they're exposed to that matters to them, or that amount of shrimp that's going to be there. Even if planners, right, they need to understand the change associated with an action. So in conclusion, I just want to reflect very briefly on what this survey and experiment suggests to me about the nature of web mapping. So, you might be thinking, well, there are many ecosystem services models that don't include a mapping component, but you could take the model output and make maps and nice maps with them, and you'd be right. But there are real challenges to that, right? So time, expertise, miscommunications. Often modelers just send decision makers what they have, right? So in Louisiana, the documents modelers are preparing for planners and the public include a lot of raw model or GIS output. There are good political economic explanations for that, but it does suggest that decision makers are shaped in how they learn with mapless ecosystem services models. And that's why I focused on interactive models in this brief survey, right? Web maps promise decision makers a certain ease of communication, relatively easy insights, but this is quite a promise. We know technical, not to mention other kinds of trade-offs exist in mapping. For instance, just in this example, limited screen space, right? Where I had to decide between having two side-by-side maps and retaining the original kind of chart view of the data. Still, decision makers could benefit from mapping dashboards that enable change comparisons, since that's often how they frame problems, their planning problems, but chain comparisons in abundant variety of ways, right, that actually work for some of the people they're interested in supporting, like shrimpers. Thank you.